So going back to the example of a memory controller. So this is register file structure. We have a 4-bit address and 16-bit decoder output. So we want to decode any one of the. So we have a 16 row of the register file. We want to select any one of that. So we have a bit line coming in. At the output, we select only one of row contents, memory contents, and so we want to design 4 to 16 decoder here. So now the question is, how many stages and how large each gate should be and how fast the decoder can operate. So we want to decide these questions. So to calculate the number of stages for best effort, the best minimum delay, so we have to calculate the past electrical effort and branching effort and etc. But these things is determined after you draw the circuit, right? Once you determine the circuit, we can calculate those parameters. And once we determine the logic gate, we add some buffer stages or whatever, so we determine the best number of stages, right? So let's see in detail in the next slide. So this is the example we haven't. For if you draw the some circuit and you determine, let's say you find the past electrical effort as 9.6 and branching effort as equal to 8, then we can calculate the past effort neglecting, if we neglect the logical effort. So meaning, so we just assume that all the inverter, the logic is just made out of the inverter chain. So we can assume that past logical effort is equal to 1. So F equal to GBH would be 96.8 from those results, right? According to that. So and find the number of stage, best number of stage is that we know that, so nth root of the 768 would be the f hat. So the best number of stage would be what? Stage 4. So we know that this is the optimum value, but we just start with the, let's say, fan out of 4. This number is not that far from the optimum, so So this is the actual example of a logic. So we have an inverter, first stage inverter, second stage is 4 input NAND gate, and last one is inverter. So we calculate logical effort and path effort and stage effort and path delay and gate size of each x and y. Okay. So logical effort, and the G inverter is 1 and 4 input NAND gate is 6/3. So total path logical effort is 2. So now the path effort is GBH. Here B is like each inverter will drive. We have a 16 output capacitance, and also 16 cases of the output line. So each line will drive 8 of them. So G is 2 and B is close to 8, and H is what? 96C over 10C. So that gives us around 154. So once we know that, the stage effort can be found in a third root of F. So that gives us the 5.36. This is a kind of a stage effort, stage delay for me to get the minimum delay in the path. Now finally, we can calculate the path delay using F hat. So minimum path delay would be 3 times F hat plus parasitic delay inverter, parasitic delay of the inverter, parasitic delay of the 4 input NAND gate, parasitic delay of the inverter. That gives us the 22.1. This is the minimum path delay for the given logic gate. Now let's find the gate size. Once we find that F hat, minimum stage effort there, so we know that stage effort F hat is defined by G times H and G times C out over C in, right? So from that C in, we can calculate C in by G times C out over F hat. So from the backward, we calculate the G first, and then we know that input capacitance of the last inverter, the G, we know the G. Once we know the G, then going back, so Y can be found. So here the equation, so 96 is the load capacitance, and 1 is the logical effort of the inverter, and 5.36 is the stage effort. That gives us the size of the G. So G input capacitance should be 18. Similarly, Y can be found. The Y input capacitance should be 6.7. So we can, in the previous example, the logic gate we arranged in a 3-stage case inverter, 4 input NAND and inverter. So using that 3-stage implementation, we get the minimum delay is 22.1. We can find the alternative way, other ways to many different ways of the cases. For example, if we start with a NAND 2 and inverter in the middle and NAND 2 inverter, with this design we get the 19.7, right? We can calculate. You can have several alternatives of the logic gate and write down and draw that, and then try to calculate the minimum possible path delay and choose the one which has the minimum delay, right? So in this case, this approach would be minimum path delay. Okay. This table gives us all the definition we had learned in this section, so you can go through and take a look at. And okay. So how we calculate how we use the logical effort. So to we use this logical effort to finally determine the size of the gate. So we are kind of starting from, we are based on the known C out versus C in. C in is known, C out. So we want to design some logic, right? So you draw some logic gate for possible stage, and then you calculate the path effort and the optimum. So rough idea. This is the rough best number of stages can be found by F, right? So fan out of 4 would be just give a rough idea. I mean, just close to optimum number. So we just try to design a circuit with the n stages, right? So for how come, now the question is, how can we calculate the f even without designing the logic? We just start with a rough idea. I mean, assume that g equal to 1 and branching some you can have some assumption how many branch would you get, and h is kind of pretty much known because the c out load versus c in is the h. So rough idea of f give us the rough idea of the number of stages. So now we accurately draw the end stage in the logic gate, and then based on, if we know the logic gate, then we can calculate the least delay, right? So least delay. So we know that once we calculate the f, we can find the best stage effort, meaning best stage delay, right? So using that number, we can backward calculate each stage's input capacitance. That gives us the device sizes, right? So far, the proposed approach has some chicken and egg problem, because so to determine the minimum path delay and also the minimum number of the stages, we have to compute the g, but even without drawing the actual circuit topology, how can we know the g? So we don't know the g, and we don't know the exact number of stages. So we just start with just rough assumption, the simple model. And also this proposed approach doesn't include the rise time and fall time kind of effect, but this is not the critical here. So also we haven't included the interconnect delay. So every line will have a RC delay that will also create give us some delay. So all the lots of iteration is required. And also maximum speed, we just calculated just least maximum speed. I mean the least delay in the path. But sometimes we also focus on the minimum area and also minimum power. So most of the time, when you design a circuit, the proposed logical effort kind of not useful most of the time. So we just rely on the circuit simulator. But what we have to remember from the in this section is that what you have to remember is that the minimum delay usually achieved by the fan out of 3 to 4, right? In this example, in this section, we just assume the fan out of 4 is the kind of a starting point. So we just, when you design something, try to make it fan out of 4, close to 4. But once you include the parasitic line parasitic, then fan out of 3 would be more appropriate in actual cases. So I just recommend students to start your circuit with the fan out of 3 with the initial design, and then later you just adjust the actual fan out based on the circuit simulator example. I mean, circuit simulator result by looking at that, and if the each stage delay is properly designed, then I mean, another thing is that once you optimize the delay here, whatever the circuit is, each stage should be similar delay, and also each stage will need to have a similar rise and fall time. If the one node is very slow by some reason, for example, you have a lot of load here, the large capacitance will be there. The other internal node will have sharp edges, but in one point, a very slow edge there, then this path is not properly designed, not well designed, because the one node is very slows down. That will degrade overall speed and power consumption, etc. So you have to watch out always intermediate node and trying to monitor that whether the delay is well balanced throughout the chain, and also the delay need to be balanced. First delay and also rise and fall time. The most of student doesn't actually check these 2 points, so most of the time design is not well optimized or well designed. So I always emphasize students to, once you design the logic, you have to monitor all the internal nodes and swing and waveform, whether that has a properly balanced or not, right? Properly balanced, one thing to note is that each stage need to have a similar fan out, right? For example, 3, if you design the fan out 3, then all the stages need to be fan out of 3. That gives us a similar delay and also similar rise and fall time. Okay, this is very important things. In summary, the logical effort so far we had learned is useful for thinking delay in circuits. So we know that NAND gates, so first numerical and logical effort can characterize gate. So logical effort for each gate represent how efficient the gate is, right, to drive the load, a certain load, right? So smaller logical effort is a good circuit. I mean, the minimum logical effort gate is the inverter, right? Inverter logical effort is equal to 1. That is the fastest one. The second best is a 2-input NAND gate. It's faster than NOR gate, since the NAND gate has a smaller logical effort than NOR gate. And passes are fastest when effort delay is close to 4, considering the parasitic delay. And also pass delay is weakly sensitive to stages and sizes. Not much variant. I mean, the variation is not that large. We remember that only 15% of only 15% of the delay, optimum delay, from the optimum delay when we choose a little different stages and sizes. So it's not that very sensitive. So another thing, critical thing is that using fewer stages doesn't mean faster path, right? You need the optimum fan out, and that optimum fan out leads us to the minimum delay. So around fan out of 4 gives us a minimum delay, so the number of stage can be found by log4 and f that give us as a minimum and the optimum number of stages. So inverter and NAND is best for driving large cap, right? So because those two are minimum the logical efforts. So inverter equal to G equal to 1 and NAND gate is G equal to what? 4/3, right? That's close to 1. So that's quite important. So most of the time you're trying to use the construct, you try to construct a logic made out of inverters and NAND gate, 2-input NAND gates. That's for best for driving large capacitance. This kind of a logical effort provides some languages. I mean, the way of discussing how we design faster circuit. But personally, I'm not so sure about this logical effort, whether we actually use this during the design process. We may understand some key important things, right, out of logical effort. So this is some tool that to understand how we design the circuit and how we size the device size for optimum and minimum delay. Just this is a tool to communicate with others, or this is just a tool for understanding the digital circuit better. Okay.